Hi, welcome back to Math 112. We are going to talk today about section 8.3, which is all about the polar form of complex numbers. So I'm going to go ahead and share my screen with you, and then we'll start with a real brief overview of complex numbers so that you're not completely lost in the weeds. This is going to be really quick, so if you're a little shaky on complex numbers, I encourage you to do a little web search or go to Math is Power 4, and that's the number 4, U, the letter U, and there you'll find a whole library of videos that are on a variety of mathematical topics, one of which you will be able to find is something on complex numbers. So we're going to get right to this. All right, you should now be able to see my iPad screen. And we are again talking about section 8.3, which is all about the polar form of complex, and actually we probably don't need Desmos because Desmos doesn't do complex numbers. So I'll bring it back if I need it. All right, so first of all, let's start with what is a complex number. And you will hopefully remember from previous classes that the imaginary number I is defined as a square root of -1, which means that I squared is equal to -1. So, for example, the square root of -9, we can think of that as a square root of -1 times the square root of 3, which means it is I times 3, or usually we write that as 3I. Okay. So a complex number is a number that has got a real part, which we usually call A, plus or minus, it doesn't really matter, a complex part, which has got an imaginary component. So A plus BI. A is the real part. BI is the complex part. Now you'll notice this is a binomial, so we have to be careful when we're squaring it or multiplying these things together to realize that it's a binomial we're working with. So we have to FOIL and do all that good stuff that we do with binomials. Any real number can be expressed as a complex number. So for example, the real number 3. That can be written as 3 plus 0i. So everything can have, every real number has a real part and a complex part, whether or not, oh, sorry, this should be an imaginary part, a real part and an imaginary part, even if you can't see it. Okay, the number, well, 3i can be written as 0 plus 3i. So all imaginary numbers are also complex numbers. All right, now, up until this point, I have always told you, and probably your other teachers have also always told you, that you cannot, if you can graph a number, it is a real number. And that is true unless we redefine our coordinate system. So that's what I want to do right now. So I'm making myself a coordinate system here. And this looks like a Cartesian system because it's based on a rectangle, on a square grid. But what I'm going to do is I'm going to label the horizontal axis as the real part and the vertical axis as the imaginary part. So what we do, so think about that number 3 plus 0i. 3 is the real part, 0 is the imaginary part. So that is the location of the number 3 plus 0i. Okay. Think about that number 0 plus 3i. We've got a real part of 0, an imaginary part of 3. So that is the location on the imaginary plane, or rather on the complex plane. So this is the complex plane. So how would I graph, do you suppose, something like -2 minus 4i? Well, hopefully you answered that there's a real part of -2 and an imaginary part of -4. So I would go to -2, -4 on the plane, and that would be the location of -2 minus 4i. So just like we redefined our coordinate system in order to graph in polar coordinates, we can also redefine our coordinate system in order to graph on the complex plane. We can make these horizontal and vertical axes represent anything we want. In this case, we've made the horizontal axis represent the real part of our complex number, and the vertical axis represent the imaginary part of our complex number. So this is how we can plot complex numbers. We define a complex plane. All right. Your textbook has got a nice overview of arithmetic on complex numbers, so I'm going to leave that for you to read and review on your own. And I want to jump right into now the polar form, because that's really the meat of this section. So the polar form of the complex number. I want you to think back to that coordinate plane I just introduced you to. The real part is on the horizontal axis. The imaginary part is on the vertical axis. Now think back to the beginning of this chapter when we talked about our unit circle. You might be able to figure out where I'm going with this. Let's see how good my fix-it thingy is here. Nope, okay. Okay, so let's think about a point on this plane. Okay, so let's just think about a point up here. Okay, that is some complex number x plus yi. It's got a horizontal component and a vertical component. If we think about building a right triangle, from the origin to that point, and we can see that this is inclined at an angle theta. If we think about this in terms of our unit circle, you see where I'm going here, don't you? I've got a radius and an x length and a y length, yes? Which means that I can talk about this angle in terms of trigonometric functions, because x can be written as r cosine theta. Y can be written as r, sine theta. And what that means then is that my x plus yi can be written as r cosine theta plus, I usually write this as ri sine theta. Okay. So this is just another way to represent a complex number. And why we go through this will be clear in just a moment. But let's talk about how to express these numbers. So let's take the complex number 3 plus 4i. And let's write it in polar form. Okay, so the other thing we need to remember is that x squared plus y squared equals r squared. Okay, so we can do a little bit of work here and figure out that if x is 3 and y is 4, that means r is 5. By this point, I'm hoping you know how to do that. That should be pretty much second nature by this point in the class. Okay, now how do I find theta? Well, I don't really need theta. I need cosine theta. So cosine theta is equal to x over r, which is 3/5. Sine theta is y over r, which is 4/5. So I can rewrite 3 plus 4i as r times cosine theta. All right, so this one's a little funky. Never mind. Sorry. We do need theta. I always forget I actually have to do this work. Okay, so if I know cosine theta is 3/5, that means that theta is the inverse cosine of 3/5. So we're going to do this in work in radians. Oh, I need Desmos, which I put away. Let's make sure we are in radians. Desmos is unhappy. Desmos is really unhappy. Give me a second here. All right, we'll use a different calculator. Oh. Okay, you're not gonna like this calculator, but it will do the job. So I need the inverse cosine. Oops, sorry. Of 3/5, which is 0.9273. Lots of stuff is unhappy. So theta, 0.9273. All right. So 3 plus 4i can be rewritten as 5 times the cosine of 0.9273, which we would turn into a number if we needed to, but in this case, I'm just illustrating this point. plus 5i times the sine of 0.9273. Okay? So now let's talk about why we would do this. And it's because of a thing called Euler's formula. So Euler was a mathematician of the Middle Ages. And what he found was that we can rewrite the polar form of a complex number. So consider a complex number z, which equals r cosine theta plus ir, sine theta. There's an alternate form for this expression, which uses the irrational number e. So we can rewrite this as r e to the I theta. And I'm not going to prove this. Proving this takes some pretty heavy-duty calculus, and it is beyond the scope of this course. You'll get to that in the next course. But we are going to utilize this. So let's think about the complex number -8. So let's find the polar form of the complex number -8. Now let's think about where that is on our complex number plane. It's got a real part of -8 and a complex part of 0, so it would be right here. -8 plus 0i. So that's at the angle pi, and the radius of the circle on which that point would lie will be 8. Okay? So the complex form, the polar form of this complex number would be 8. So I want to think about z equals r e to the I theta. R equals 8. Theta equals pi. So -8 can be rewritten as 8e to the pi I. And if you have a calculator that can do complex numbers, which your TI-84 can do, Desmos cannot, but your TI-84 can, then you can check that. And you will, sure enough, get -8. Okay? Let's try one that's a bit more complicated. Let's try doing the same thing with the complex number z equals -3 minus 5i. All right, so we think about where that is on the complex plane. It's got a real part of -3 and an imaginary part of -5, so it'll be right down here. And my angle theta, and this is my r. Okay, so let's start with finding r. So r is equal to the square root of x squared plus y squared. So r equals square root of 34. All right, now there's a couple of different ways to find our angle theta. We can use inverse cosine, we can use inverse sine, or we can use inverse tangent. So remember that the tangent of any angle is equal to the y coordinate divided by the x coordinate. So theta is going to be equal to the inverse tangent of 5/3. If you plug that into your calculator, you will get 1.0304. Now we just need to do a quick mental check and see what coordinate that puts us in. Well, 1.0304 is less than pi. In fact, it's less than pi over 2. So that puts us up here in the first quadrant. We need the third quadrant answer. So my angle is actually at this number plus pi, which will be 4.1720. So we would rewrite our -3 minus 5i as r times e to the I times theta, so 4.1720i. Now you may be asking yourself, why in the heck? Well, let's do one more thing and then I'll tell you why in the heck. So let's go the other way. So let's think about the complex number e to the pi over 6i and write this in a plus bi form. What do we know? Well, looking at this, whoops, there's a 3 in front of that. Z equals 3e to the pi over 6i. So what do we know? Well, we know that the polar form is always re to the I theta. So r must be 3. Theta must be pi over 6. So we can rewrite this as r cosine theta plus ri sine theta but pi over 6 is one of our special known values, so we know that the cosine of pi over 6 is √3/2. And we're in first quadrant, so both sine and cosine are going to be positive. So sine of pi over 2 is 1/2. 3 times 1/2 is 3/2. Don't lose the I. Okay. Now, why in the heck would we want to do this? Well, let's talk about that. Suppose I ask you to evaluate something like -4 plus 4i to the 6th power. Why don't you find that value? Well, we could do some work and do some multiplication with binomials and eventually get here, right? If you want to try that, I'll leave it to you. You could maybe plug it into your calculator, but it might or might not give you the right answer. So let's see what would happen if we converted this into polar coordinates. In the interest of time, I'm going to tell you that converting this into polar coordinates is in your textbook. It's on page 532, I think. But so I'm just going to give it to you. I'm going to leave it to you as an exercise. You do it just like I did the last one, next to the last one. And what we find is that this can be rewritten as 4 times the square root of 2 times e to the 3 pi over 4i, all to the 6th power. That's better, isn't it? Because that thing on the right-hand side, we can use the product to a power rule and realize that this simplifies to 4 to the 6th power times the square root of 2 to the 6th power times e to the 6 times 3 pi over 4 I. Hopefully you remember your rules of exponents and you remember how to do that. Now 4 to the 6th, I don't know that number. So 4 to the 6th power is 4096. The square root of 2 to the 6th power is 2 to the 3rd power, which is 8. And that's e to the 3 pi over 2 times I. No, it's not. 9, wait. 18 over 4 simplifies to 9 over 2. That's better. Let's take our 4096 multiplied by 8, and then we get 32,768. $32,768. Double check that, make sure that I wrote that down correctly. Yes, I did. Times e to the 9 pi over 2I. Now remembering that that is an re to the I theta. So I want to go back to a plus bi form. So we know that r is 32,768. Theta is 9 pi over 2. And we can write our complex number, z, as 32,768 times the cosine of theta, which is 9 pi over 2, plus 32,768I times the sine of 9 pi over 2. 9 pi over 2 is a known value, and the cosine of 9 pi over 2 is 0. So this is 32,768 times 0. The sine of 9 pi over 2 is 1. So this is going to be I times 32,768 times 1. And what we find is that -4 plus 4i to the 6th power is equal to 32,768 I. Okay, this is why we use the polar form of complex numbers. This will also allow us to do things that we can't do any other way, like find the square root of 9i. And the way that you would do that is you would write your z. You would think of 9i to the 1/2, or sorry, square root of 9i as 9i to the 1/2. You would convert your 9i into polar form and then apply an exponent of 1/2. And this is also in your textbook. It's example 13. And this video has gone as long as I want it to go. So I'm going to stop here. I'm going to commend the rest of your textbook section to your study. You're now ready for the 8.3 homework, and please, please contact me if you have any questions at all. Thanks, and have a great day.